Welcome to The Deep Dive, the show that extracts the most important nuggets of knowledge to get you truly well informed. Today, we're plunging into a topic that's not just foundational to the internet, but one that has been silently solving a growing crisis for years. IPv6.
That's right.
Its story really starts with the internet's explosive, almost unbelievable growth.
Indeed. It's a crisis that unfolded largely beneath the surface for most people, yet it touched the very core of how our connected world operates. We were frankly running out of internet addresses.
That's a mind-bending thought, isn't it? Running out of addresses on the internet.
It really is.
You know, when it started, the internet was a niche academic tool, right? A handful of connected institutions.
Exactly. Very small scale.
Then, almost overnight, it became this global phenomenon connecting billions. And that rapid, unforeseen growth created a massive architectural problem for its original addressing scheme, IPv4.
IPv4, yeah. With its 32-bit addresses, it provided approximately 4.3 billion unique addresses. When it was designed back in the late 70s, early 80s, that number truly seemed, well, comically infinite, as one of our sources put it.
Comically infinite, I like that.
The idea that every person, let alone every device, would need a unique, publicly accessible address was, pure science fiction at the time.
But science fiction became our reality, and it happened fast. By the early 2010s, the alarm bells were ringing loud and clear across the globe.
Oh, definitely.
Regional Internet Registries, or RIRs, these are the organizations responsible for handing out blocks of IP addresses, they began exhausting their pools.
That's right. APN, serving the Asia-Pacific region, hit its limit in April 2011.
Wow, 2011 already.
Yeah. RPENCC, for Europe, the Middle East, and Central Asia, followed in September 2012. And then AON, for North America, reached its final allocation in September 2015.
So the dominoes were falling pretty quickly there.
They really were. This wasn't just a minor technical hiccup. It was a fundamental supply chain problem for the internet.
Supply chain problem, that's a great way to put it.
Yeah. If you can't easily get new, unique IP addresses, you severely hinder the ability to bring new devices, new users, and entire new networks online with full functionality. It signaled a foundational architectural bottleneck for our digital future.
And that, is exactly where IPv6 steps in. It's the necessary, foundational, next-generation protocol designed not just to solve this crisis, but really to modernize the entire network layer.
That's the goal, yes.
Our mission today is to demystify IPv6 for you. We're going beyond just more addresses. We're going to explore its core architecture, how it fundamentally redesigns the network layer for greater efficiency, built-in security, and streamlined operations, and why it's absolutely crucial for the future of our connected world.
So by the end of this deep dive, you'll have a clear, well-informed understanding. That's the plan.
Exactly. To guide us, we've pulled from a diverse stack of sources. We've got technical presentation slides from IPv6, Deep Dive Share Session 11.1 and 64 by Applied Expert Systems, Inc., giving us those foundational technical specifications.
Right, the nitty-gritty details.
And we're also leaning on comprehensive industry tutorials from Catchpoint and Geeks for Geeks, which really help clarify complex concepts like multicast and header structure.
Those are super helpful for breaking things down.
Plus, we've incorporated some fascinating real-world perspectives and a touch of the human element from a Reddit discussion titled, "What's the Deal with IPv6 and Why is it so complicated?"
Ah, yes. That should provide some candid insights into the challenges and perceptions surrounding this transition.
Definitely. So with that, let's unpack this.
Let's do it.
Let's start with the big why. Why did we need IPv6 in the first place? What were the fundamental limits of its predecessor, IPv4, that truly necessitated such a dramatic internet-wide change?
Right. It really boils down to what we've called the triumph and tribulation of IPv4. When IPv4 was conceived in the late 1970s and early 1980s for ARPANET, it was, by all accounts, an elegant, robust, and brilliantly functional system.
For its time, absolutely.
Yeah. For its time, yes. Its core was that 32-bit address space, which works out to precisely 4,294,967,296 unique addresses. For a network of a few dozen institutional computers, as you mentioned, this seemed practically endless. It just wasn't built for a global public.
And then the internet just exploded. It far exceeded anyone's wildest expectations.
Completely.
The 1990s brought the World Wide Web, transforming it from a niche academic tool into a global commercial and social phenomenon. Personal computers started appearing everywhere, each needing an IP address to connect. That was sort of the first wave.
But the real tsunami, as one of our sources aptly describes it, came in the late 2000s and 2010s with the mobile revolution.
Ah, yes, smartphones.
Exactly. Suddenly, it wasn't just desktop computers, it was smartphones, tablets, and billions of new laptops that people carried everywhere. And now we're deep into the era of the Internet of Things, or IoT.
Right, where everything needs an IP.
Literally everything, from smartwatches and home assistants to industrial sensors and traffic lights, demands an IP address. This is what transformed that once comically infinite IPv4 pool into something that felt, well, terrifyingly finite.
Terrifyingly finite. And we saw the results of this firsthand with the regional address exhaustion across the globe.
We did.
APNIC, Asia Pacific, ran out in April 2011. RIPE NCC, Europe, Middle East, Central Asia, September 2012.
Then Oceanic in Latin America and the Caribbean, June 2014.
Aeon in North America, September 2015.
And Afrinic, for Africa, was the last to run dry, entering its final phase of exhaustion in 2017.
These dates aren't just statistics. They're milestones marking a growing crisis that spanned the globe.
You've put it well. The well was quite literally dry. We had a foundational problem that demanded a new approach.
So what did network engineers do when they saw this coming? They couldn't just stop connecting things. They came up with a stopgap solution, network address translation, or NAT.
NAT, yeah.
And it was, in its own way, a truly ingenious workaround that bought us decades.
It genuinely was. NAT was a clever and highly effective workaround that prolonged IPv4's life significantly. It's the reason your home, for example, can have a dozen devices, laptops, phones, smart TVs, gaming consoles, all connected to the Internet through a single public IPv4 address that your Internet service provider gives you.
How does it actually work at a technical level? For those of us who might not be network engineers, give us the quick version.
Certainly. Your home router typically receives just one public IPv4 address from your ISP. Inside your home, the router creates a private network, often using addresses from non-routable blocks like 192.168.x.x.
Familiar territory for many.
Very familiar. When your laptop, which has one of these private IPs, wants to access a website on the Internet, it sends the request to the router. The router then translates your laptop's private source address into its own public Internet-facing address. It sends the request out, and crucially, it keeps a record of this translation in something called a state table.
Okay, like a little ledger.
Exactly. When the website's response comes back, the router consults its table, sees which internal device the traffic is for, translates the destination address back to your laptop's private address, and delivers the packet.
That's a great way to put it. So the router is almost like a very clever post office. All the letters inside your house have a private internal address, but when they leave, the post office puts its own public address on the envelope and then meticulously reverses the process on the way back in.
That's a very apt analogy.
It must have conserved public IP addresses on a massive scale.
It did exactly that. However, while ingenious, NAT is fundamentally a patch, not a cure. And it introduces significant problems and hidden costs that we're still grappling with.
Okay, what are those hidden costs? Where did NAT fall short? Because it seemed to work for a long time.
Well, first, and perhaps most importantly, it breaks the end-to-end principle.
The end-to-end principle. What's that exactly?
The original architectural vision of the Internet was beautifully simple. Any device should be able to directly send a packet to any other device. NAC shatters this. Devices behind a NAT are not directly addressable from the outside world.
Ah, so they're hidden.
Exactly. This fundamentally hinders applications that rely on direct inbound connections, like many forms of online gaming, peer-to-peer file sharing, direct video conferencing, and even hosting services where you want external access to a server on your internal network.
That makes perfect sense. I remember the pain of setting up port forwarding for online games years ago, and that was precisely because of NAT.
Oh, yes. Port forwarding.
You were trying to punch a hole through that post office wall, so to speak.
Precisely. Secondly, it adds significant complexity and fragility to the network. NAT requires routers to perform complex stateful inspection and manipulation of every single packet that passes through.
Every single packet?
Every single one. This consumes valuable processing power and memory on the router. It can also interfere with certain protocols, especially those that embed IP addresses in their data payload, requiring even more complex workarounds called application-level gateways, or ALGs.
The ALGs, right. Those can be tricky.
They can. It's a lot for a router to do constantly.
So the router isn't just mindlessly forwarding packets, it's actively inspecting and rewriting every packet's address. That sounds like a lot of work and a potential point of failure.
It absolutely is.
Yeah.
And finally, NAT hinders troubleshooting and logging.
Yeah, I can see that.
When multiple devices on an internal network share a single public address, it becomes incredibly difficult to trace malicious activity or even simple network issues back to a specific source device.
Oh.
This complicates security investigations and basic network diagnostics immensely.
Right. Imagine trying to find out which person in a large office used a specific external service when everyone appears to come from the same IP address. It'd be a nightmare.
Exactly, a total nightmare for forensics.
Okay, so NAT bought us time, but it came with some serious trade-offs and headaches for developers and network administrators. The internet clearly needed a real long-term solution. It needed more addresses.
Fundamentally, yes.
And that, I'm guessing, brings us to the core promise of IPv6, a universe of addresses.
This is truly the most dramatic and visibly impactful change. The shift from 32-bit addresses in IPv4 to 128-bit addresses in IPv6 is a leap in scale that's genuinely difficult for the human mind to fully grasp.
It really is an exponential jump.
A huge one.
I mean, 128 bits sounds like a lot, but what does that actually mean in terms of available numbers? Can you even say the number?
A 128-bit number allows for 2 to the power of 128 unique addresses. That number, when written out, is an astounding 340,282,468,963,463,463,468,711,456.
Okay, just hearing that number is overwhelming.
It is. It's typically stated as 340 undecillion or 3.4 by 10 to the power of 38. That's a 340 followed by 36 zeros.
Undecillion. Wow, that number is just astronomical. How do we even begin to grasp that scale? Can we use analogies to wrap our heads around it?
Analogies are really the only way to convey this immense scale. For instance, scientists estimate there are about 7.5 by 10 to the power of 18 grains of sand on Earth.
Okay, that's already a huge number.
It is. With the address space of IPv6, you could assign approximately 45 quadrillion unique IPv6 addresses to every single grain of sand on the entire planet.
Whoa! Every grain of sand. 45 quadrillion times. That's utterly mind-boggling. That's a truly physical representation of limitless.
It really puts it in perspective. Or, if you prefer a cosmic scale, the observable universe is estimated to contain about 2 by 10 to the power of 23 stars.
Okay.
IPv6 provides over 1.5 trillion unique addresses for every single star in the observable universe.
Okay, so universe of addresses is not an exaggeration. That is truly infinite for any practical purpose we can imagine for centuries to come.
Pretty much, yeah.
It's designed to future-proof the internet for a scale that's almost unimaginable right now.
Exactly. This vastness is not just for show, it's a deliberate design choice. Its primary purpose is to restore the Internet's original end-to-end principle, which NAT had fundamentally broken.
Bringing back that original vision.
Right. It also explicitly enables the future growth of the Internet, particularly for the countless billions of IoT devices that each need unique, publicly routable addresses without the complexities and limitations that NAT created.
So IPv6 isn't just about adding more numbers to the internet. It's about fundamentally re-architecting how devices connect, communicate, and scale. It's truly a new language for a new era of connectivity.
It absolutely is. And that immense address space comes with new rules for how addresses are written, structured, and used, which brings us directly to the practicalities of this new language.
Okay, so we're talking about this universe of numbers now, 128 bits to be exact. That's a huge leap from IPv4's 32 bits. The scale shift is obviously the most dramatic and necessary change, but how do we even write these addresses? IPv4's dotted decimal notation certainly won't cut it.
You're absolutely right. It won't. IPv6 addresses are far too long for that. Instead, they're written in hexadecimal notation.
Yeah, hexadecimal.
The 128 bits are divided into 8 16-bit blocks. Each 16-bit block is then represented by 4 hexadecimal digits, and these blocks are separated by colons.
So an unabbreviated IPv6 address would look something like 2001.00000.858.00000.85A3.00000.4C000.870.00000 and feels a bit unwieldy.
That's where the life-saving abbreviation rules come in, which are truly crucial for making IPv6 manageable and, more user-friendly. There are 2 main rules.
Okay, what's rule number 1?
Omission of leading zeros. In any 16-bit block, any leading zeros can be removed. Think of it like writing the number 5 instead of 0005.
Simple enough.
So 0db8 becomes db8 through 0370 becomes 370, and a block of all zeros, thousands, simply becomes 0. It's important to remember, though, you cannot remove trailing zeros, only those that precede the significant digit.
Got it. So our example address, 2001.000.000.80.82e.83.0370.7334. After applying that first rule would become 2001.db8.85a3.8 A2E.370.7334. Much better already.
Definitely shorter.
What's the second rule? This is where here it gets really clever.
The second rule is the double colon compression, represented by cup hierarchy. Many IPv6 addresses contain long, contiguous sequences of all zero blocks. To simplify this, a single contiguous sequence of all zero blocks can be replaced by a double colon.
So you're saying if I have 0.0.0, I can just write low band A. That's a massive shortcut.
Precisely. But here's a crucial part, and this is stressed in our sources for good reason. This can only be done once per address.
Only once? Why is that?
If you used it more than once, it would be impossible for the system to know how many zero blocks were compressed in each instance, leading to ambiguity. The system wouldn't know how to reconstruct the full address.
That makes sense. It needs to be unambiguous for the computer. So going back to our example, 2001.db8.85a3 to 0.8e.370.7334, we have two consecutive zero blocks. We could replace them with a double colon, making it 2001.db8.853.82e.370.7334. That's significantly shorter and much more readable.
Absolutely. Or consider phi80.000.000.004.61ff.f9t.f156.
Okay.
Then with the double colon compression, it becomes phi80.204.61ff.fnd.f9t.f156.
Okay.
Then with a double colon compression, it becomes phi80.204.61ffs.f9t.f156, where the F1 represents those three compressed zero blocks. It's quite elegant once you get used to it.
It definitely cleans it up. Okay, so that clarifies how we write them, but why hexadecimal and colons? Our Reddit source had some interesting discussion on this, beyond just handling the length.
Indeed. The choice of colons over dots, for instance, prevents ambiguity, especially in a mixed environment or if an address happened to end like a country code top-level domain, say .de looking like .de.
Ah, okay, so it avoids conflicts with DNS resolution and ensures clear parsing for machines.
Absolutely. And hexadecimal provides a consistent 4-character representation for each 16-bit block. Decimal representation, as used in IPv4, can vary from 1 to 3 digits per octet, which makes parsing more challenging for systems.
Right, the length varies.
Plus, as one Redditor humorously pointed out, it prevents systems from misinterpreting IP addresses as currency or other numeric formats in spreadsheets. You can just imagine that Excel nightmare.
I certainly can. Trying to sort IPs and getting dates instead. Now, even with 128 bits, is it just one giant flat number, or is there some structure to it, like IPv4's network and host portions? That's critical for how the internet routes traffic efficiently.
That's an excellent and crucial question, and it brings us to the 3-part harmony of the standard IPv6 address structure. Despite being a single 128-bit number, IPv6 addresses are indeed hierarchically structured, even more deliberately so than IPv4, to facilitate efficient routing.
So it's not just a big pile of numbers. Good. What are these 3 fundamental parts?
First, we have the global routing prefix, which is usually 48 bits long. This is essentially the network portion, assigned by an ISP to a customer or an entire site, like your company's network or your home internet connection.
So like the main address block for a whole organization.
Exactly. It's globally unique and allows internet routers anywhere in the world to forward packets to the correct destination network. Think of it like the country and major city part of a postal address, telling the mail where to generally go across vast distances.
Okay, that makes sense. What's next?
Next is the subnet ID, which is usually 16 bits. This portion is controlled by the local network administrator. It allows an organization to create a vast number of subnetworks within its site.
16 bits for subnets. How many is that?
With a full 16 bits, an organization can create up to 2 to the power of 16, or 65,536 individual subnets.
Wow, 65,000 subnets inside a single organization. That's an incredible amount of room to grow and organize, far beyond what most IPv4 networks ever envisioned.
It truly is. This incredibly generous allocation really helps with logical and scalable network design, freeing us from the constant constraints and complex calculations of IPv4 subnetting.
That sounds like a relief for network admins. And the last part.
And finally, we have the interface ID, which is always 64 bits. This is the host portion, uniquely identifying a specific device's network interface within a given subnet.
Always 64 bits. That's interesting.
Yes, that fixed 64-bit structure is a key design choice. It simplifies routing and address management significantly because routers only care about the first 64 bits to route to the subnet, and the rest is for the local link. The interface ID can be generated in various ways, for example, from a device's MSE address using the UI64 process, or randomly for privacy reasons using privacy extensions.
So that fixed 64-bit interface ID is critical. Does this hierarchical design lead to significantly more efficient routing across the internet?
Absolutely. This structured allocation, typically using a 48 prefix for organizations and a 64 for individual subnets, drastically reduces the number of entries needed in global internet routing tables.
Fewer routes for the big routers to worry about.
Exactly. This, in turn, improves overall internet performance because core routers don't have to process as much information to make their forwarding decisions, leading to faster packet delivery.
That sounds like a powerful change that goes beyond just having more addresses. It's about how the addresses are organized and used for a much more efficient internet backbone.
It truly is a fundamental redesign that optimizes for both scale and speed, and that efficiency extends beyond the address structure into the very packets themselves.
Okay, so we've talked about the enormous address space and the new hexadecimal language of IPv6, but the redesign goes even deeper, all the way down to the packet header itself. This is where we see some serious streamlining compared to IPv4, right?
Absolutely. The IPv6 header is a significant improvement over IPv4, embodying the principle of lean and fast. The key takeaway here is that it's a fixed size of 40 bytes.
Fixed at 40 bytes, that seems quite small.
It is, compared to the potential size of IPv4 headers. This is a much simpler and more consistent structure than the variable-length IPv4 header, which could swell with optional fields. This fixed size dramatically speeds up processing for every router that handles the packet.
Because the router knows exactly where everything is every time.
Precisely. No need to figure out how long the header is first.
What specifically was removed from the IPv4 header to achieve this leanness and efficiency?
Several fields that were either redundant or created processing bottlenecks in IPv4 were removed. For instance, the header length IHL field was eliminated because with a fixed 40-byte size, there's simply no need to specify its length anymore. That's one less thing for a router to check.
That makes perfect sense. What about fragmentation? That was a fairly complex and resource-intensive part of IPv4.
That's one of the most radical and impactful changes in IPv6. The fragmentation field identification, flags, and fragment offset were entirely removed from the base header.
Completely gone.
From the base header, yes. In IPv4, any router along the path could fragment a packet if it was too large for the next link. This is computationally expensive, as routers have to spend cycles breaking down packets. In IPv6, routers do not fragment packets. This is a critical distinction.
Routers don't fragment. So if a packet is too large for a link, what happens instead? Do they just get dropped?
Precisely. If a source sends a packet that is too large for a link along the path, the router simply drops it and sends an ICMPv6 packet too big message back to the source.
Ah, okay. ICMPv6 again, so it tells the sender.
Exactly. The source host then receives this message, adjusts its packet size to a smaller path-friendly maximum transmission unit, MTU, and retransmits the data in smaller packets. This design decision offloads the computationally expensive work of fragmentation entirely from core routers to the network edge, where the source host resides.
Which speeds up forwarding significantly for the entire network, presumably.
Hugely. So the core routers can just focus on routing, not on the computationally heavy task of managing fragmentation. It's a huge efficiency gain, shifting the burden to the devices that generate the traffic.
Makes sense. What else got cut?
Another significant removal was the header checksum. In IPv4, this checksum had to be recalculated at every single hop because the time to live, or TTL field, was decremented at each router.
Right. Changing the header meant recalculating the checksum.
Exactly. This recalculation was a major processing bottleneck. Given modern network reliability and the fact that checksums are still performed at upper layers like TCP and UDP, and at the data link layer like Ethernet, the IPv6 header checksum was deemed redundant and inefficient.
So trusting the other layers to catch errors. Okay. So if the header is leaner, what new or improved fields did IPv6 introduce to enhance functionality or replace some of those removed?
The IPv6 header has some very clever additions for a more modern internet. We still have the version field, which is 4 bits and always identifies the protocol as 6N, binary 0111.
Okay, that's straightforward.
The traffic class field, an 8-bit field, is similar to IPv4's service field, but with more explicit intent. It indicates packet priority, for example, allowing values 0-7 for congestion-controlled traffic, while 815 are for uncontrolled traffic like real-time audio and video, which often get higher priority. This helps routers decide which packets to drop first during congestion or how to prioritize traffic.
I see. So it explicitly helps with quality of service, QoS, right in the header. That seems like a big step up.
It is, offering much more granular control. Then there's the flow label, a 20-bit field. This is a powerful new addition used by a source to label packets that belong to the same flow or stream of data.
A flow, like a video stream or a file transfer.
Exactly. By marking packets with a consistent flow label, the source can request special handling, such as a specific quality of service, from intermediate routers. A zero value simply indicates default handling. This helps applications like streaming video maintain consistent high performance across the network.
Clever. And what about the payload length?
That's a 16-bit field indicating the total size of the payload, which includes any extension headers plus the upper layer packet, like TCP or UDP. If the payload is extraordinarily large, greater than 65,535 bytes, which is rare but possible, this field is simply set to 0, and a jumbo payload option is then used in a special hop-by-hop extension header to indicate the true larger size.
Okay, so it can handle truly massive packets when needed, even though it's rare, using that extension header trick.
Yes, through that clever mechanism. Then we have next header, an 8-bit field which identifies the type of the very next header following the main IPv6 header. This could be another extension header or the upper layer protocol like TCP value 6 or UDP value 17.
So it tells the receiver what comes next.
Precisely. And finally, the hop limit, an 8-bit field that directly replaces IPv4's time to live, TTL. It's decremented by 1 at each node and forwards the packet. And if it reaches 0, the packet is discarded, preventing infinite loops on the network.
Okay, so similar concept to TTL, just a different name.
Essentially, yes.
So the main header is lean and fast, but you mentioned extension headers. What's the deal with those, and how do they keep the core efficient while still allowing for rich features?
The power and elegance of extension headers are a core part of IPv6's design. They replace IPv4's single, flexible, but often complex and variable length options field. In IPv6, optional information is placed in separate, chained extension headers that follow the main header.
Chained together, like building blocks.
Exactly. The beauty of this is that routers typically only need to examine the main 40-byte header to make their forwarding decisions. They can completely ignore most extension headers, passing them on without inspection, unless they are the final destination or the extension header specifically tells them to do something, like the hop-by-hop header.
So the base header is always fast, and if there's extra optional information, it's just attached in a modular way that routers can largely bypass if they don't need it.
Exactly. This design makes the base header lean and fast, while still allowing for rich extensibility without compromising performance. Common examples include the hop-by-hop options header, which, as its name suggests, is processed by every router. The routing header, used for source routing. The fragment header, used by the source for fragmentation if needed.
Ah, so that's where fragmentation lives now.
Precisely, in an extension header, only added by the source if necessary. And crucially, the authentication header, AH, and encapsulating security payload, ESP, which provide IPsec security and are integral to IPv6's security posture.
That's a really smart way to keep the core efficient while still supporting advanced features and future extensibility. It's like the main envelope is always simple, and if you have special instructions or secure content, you just add another smaller, clearly labeled envelope inside that only the recipient or specific couriers need to open.
A perfect analogy. This modularity is a hallmark of IPv6's design for future-proofing and unparalleled performance.
We've covered the architectural changes in IPv6 addresses and headers, but let's dive into the different types of IPv6 addresses themselves. It's not just about simple one-to-one communication anymore, is it? It feels like there's a much richer vocabulary for how devices can talk to each other.
Not at all. IPv6 introduces a much richer and more nuanced system of address types and scopes compared to IPv4's simpler public-private broadcast model. Understanding these distinct types is absolutely key to understanding how IPv6 operates and its underlying design philosophy.
Okay, let's start with what most people are probably familiar with. One-to-one communication or unicast addresses. What are the key variations there?
A unicast address identifies a single, unique network interface, and a packet sent to it is delivered to that specific interface only. Within unicast, we have several important categories.
First, the global unicast address, or GUA. What's that, in simple terms?
The GUA is prefixed 2000.3, meaning any address starting with binary 001. Effectively, this covers hexadecimal addresses from 2000 up to 3FFF in the first block. These are the public Internet Routable IPv6 addresses, directly analogous to the public IPv4 addresses you might get from your ISP. Think of it as your full, unique postal street address. It can be used to send you mail or data from anywhere in the world.
So when my device talks to a website over IPv6, it's typically using a GUA. What about link local addresses, LLAs? I hear those are mandatory and quite fundamental.
They absolutely are. LLAs use the prefix fee80.0. This is one of the most important concepts in IPv6. An LLA is an automatically generated address that is mandatory for every IPv6-enabled interface.
Every single one.
Every single one.
Yeah.
And it's valid and usable only on a single network segment or link, like just the devices connected to the same Wi-Fi network or Ethernet switch.
Yeah.
Crucially, routers absolutely do not forward packets with an LLA as a source or destination to other networks.
So they stay local.
Strictly local. They're used for local conversations between neighbors and with the local router. They're essential for the Neighbor Discovery Protocol, or NDP.
So it's like saying, the person in the blue shirt in this room, only meaningful in that specific context, not across the building or across town.
That's a perfect analogy. Without it, core protocols like Neighbor Discovery wouldn't function. Then there are unique local addresses, ULAs, with prefix FC00.7, specifically FD00.8 for locally generated ones.
Always. Okay.
These are the official replacement for IPv4 private addresses like 192.168.x.x. They're intended for internal communications within a site or organization and are explicitly not routed on the public internet.
So an internal mail stop code or cubicle number within a large corporate campus that isn't publicly known, like the private IPs we use now.
Exactly, but with a twist. What's fascinating here is that while they're private, ULAs are designed to be globally unique, even for private use.
It's globally unique but private. How does that work?
It's achieved by incorporating a random 40-bit global ID into the prefix, specifically in the FD0.8 range. This design virtually eliminates the problem of overlapping internal address spaces, which is a common and expensive headache in IPv4 networks, especially during corporate mergers or VPN connections between different private networks using the same 192.168.1.x.
That makes so much sense. No more IP conflicts when connecting networks. That's a huge benefit for large organizations. Are there any other special unicast addresses worth noting?
Yes, a couple more. The loopback address, point 1, is the IPv6 equivalent of IPv4's 127.0.0.1, used by a device to send packets to itself for testing software or network services. And the unspecified address, which is all 128-bit 0, is used only as a source address by a device that hasn't yet been assigned a proper IP address, for example, during its initial SLAAC or DHCPD6 setup phase. It's a temporary who am I address.
Okay, so that's unicast one-to-one communication. But IPv6 truly shines with its multicast addresses, which are all about one-to-many communication, and this is described as a core improvement over IPv4's broadcast rate.
Absolutely foundational, and it's a massive leap in efficiency. Multicast addresses use the prefix FS00.8. A multicast address represents a group of interested receivers. Packets sent to this address are intelligently delivered only to interfaces that have explicitly subscribed to that group.
And this completely replaces broadcast, which IPv4 relied heavily on. I remember broadcast storms being a real issue.
Exactly. IPv6 has no broadcast addresses. Multicast completely replaces the broadcast function. This is a huge efficiency gain for the network. In IPv4, a broadcast packet is sent to every single device on a local network, forcing all of them to process it, even if they're not interested.
Wasting CPU cycles everywhere.
Right. This creates unnecessary traffic and can lead to those broadcast storms that cripple network performance. With IPv6 multicast, traffic is delivered only to interested parties, significantly reducing network chatter and CPU overhead on devices that don't care about that particular traffic.
So for applications like video conferencing with multiple participants, VoIP calls with many listeners, or live video streaming, this means a massive improvement in network efficiency and scalability. You're not spamming everyone.
Indeed. Instead of a source sending multiple unicast streams or a single broadcast stream that everyone has to process, each device sends a single stream of packets to a single multicast destination address. The network intelligently duplicates and forwards these packets only to the specific devices participating in that specific multicast group.
So it's like sending a targeted email to a mailing list of interested subscribers, rather than shouting a message out to an entire stadium, forcing everyone to stop and listen. That's a really clear distinction.
A perfect analogy. A very practical example of its use is how the Neighbor Discovery Protocol, NDP, which we'll discuss more soon, uses solicited node multicast addresses to resolve MAC addresses. Instead of broadcasting to everyone like ARP does, a device sends a multicast query only to a specific group that only the target device is listening to.
So much quieter on the network.
Exactly. It allows other devices to completely ignore the packet at the network interface level.
That's very clever. It reduces the noise on the network. Our sources also detailed the structure of these multicast addresses, both old and new formats. Without getting into every single bit, what's the key takeaway about their design?
The essential structure of a multicast address, old format RFC 2373, includes an 8-bit prefix 0xFF, which flags it as multicast. Then there are 4-bit flags indicating if it's a well-known or transient group, and a 4-bit scope field that defines how wide the multicast network is, for example, link local, site local, organization local, or global.
Scope. Okay, so you can control how far it travels.
Precisely. The rest is a 112-bit group ID. The newer format, RFC 7371, is an extension, adding more specific flags and fields for future proofing and richer context like the R, P, and T flags for rendezvous point, prefix information, and transient status. The key insight is that IPv6 multicast is designed to be highly flexible and scalable, allowing for precise control over group membership and distribution.
So more granularity for future advanced services. And we saw an example of deploying this with Cisco routers, setting up a rendezvous point and a bootstrap writer, with a host joining a multicast group FF07.7. This demonstrated how a ping from the source successfully reached the receiver, illustrating that one-to-many communication.
That example clearly showed how IPv6 multicast routing is enabled on all devices, and how a router can be configured as a candidate, RP, rendezvous point, and another as a BSR, bootstrap router, to dynamically choose the RP. The host then uses a command, usually involving MLD, multicast listener discovery, to subscribe to a specific multicast group, and the system delivers the ping packets efficiently and only to the members. It's a very robust system.
One question that comes to mind. Can multicast traffic cross the public internet, or is it primarily for internal networks?
That's a great question. Generally not natively. Most ISPs will by default drop any packets with a multicast destination address due to the potential for excessive bandwidth demands on their public networks.
Right, you wouldn't want one stream flooding the internet.
Exactly. So it's typically restricted to internal enterprise networks or specific academic research networks. It can be tunneled over the internet for remote site participation, effectively encapsulating the multicast traffic within unicast tunnels, but it's not natively transmitted end-to-end across the public internet today.
So it's technically possible, but not the standard way things work.
Correct. There was an experimental IPv4 GLOP multicast address space, 233.0.0.08, that attempted to use ASNs for allocation, but it was too limited and not widely adopted. IPv6 Global Scope Multicast, ACXE Bates16, offers a much larger address space with potential for future internet-wide use, though adoption is currently slow for that global scope.
So it's a powerful tool, but primarily for within a network for now, unless you're using tunnels. Lastly, what about anycast addresses? What's this one-to-nearest communication? That sounds intriguing.
Anycast is a truly fascinating hybrid of addressing. It's a single address that is assigned to multiple devices, typically servers in different physical locations. The magic happens when a packet is sent to an Anycast address.
The same address on multiple machines.
The exact same address. The network's routing infrastructure, using its knowledge of network topology, delivers the packet to only one of those interfaces. Specifically, the one that is closest in terms of routing metrics.
So like root DNS servers, for example, the same IP address, but you're directed to the one closest to you physically.
Exactly. That's the prime and most critical use case. The same Anycast IP address for a root DNS server, for instance, can be advertised from dozens of locations globally. This directs a user's DNS query to the nearest available server.
Which improves speed and resilience.
Massively. This design provides incredible benefits. High availability, redundancy, and low latency for users by always connecting them to the optimal and closest resource. If one server goes down, the network automatically routes you to the next closest one using the same address.
No, it's like dialing a generic customer service hotline, say 800 PZA, and your call automatically ranks to the geographically closest call center without you even knowing it. That makes it incredibly robust.
A perfect analogy. Anycast is critical for distributed, resilient services on the internet that demand both speed and reliability.
We've explored the addresses themselves, from unicast to multicast and anycast. But now let's look under the hood at the engine room of IPv6. What are the core protocols and mechanisms that make this new internet language actually work? And first up, SLAAC. Stateless address autoconfiguration. This is described as the magic of self-configuration.
It truly is a standout operational improvement in IPv6, simplifying network administration enormously.
Ah.
SLAAC allows a device to automatically configure its own valid, globally routable IP address the moment it connects to a network.
Automatically, without asking anyone.
Essentially, yes.
Yeah.
This happens without any manual setup or even needing a DHCP server. It's basically plug and play for getting an IP address.
That sounds almost too good to be true. How does a device just magically get an address without a central server? Can you walk us through that step by step?
Absolutely. It begins the moment a device's network interface activates. First step, generate a link local address, LLA. The device first creates its own LLA by combining the FE80.10 prefix with a 64-bit interface ID, often derived from its MEAC address or generated randomly for privacy.
Okay, so it makes its own local address first.
Right. Crucially, it then performs duplicate address detection, DAB, by sending out a neighbor solicitation for its own potential LLA to ensure no other device on the local link is already using it.
Checks if the coast is clear.
Exactly. Second step, router solicitation, RS. Once it has a unique LLA, the device sends a router solicitation RS message. It multicasts this RS message to the all routers multicast address, FS02.2. It's essentially asking, are there any routers here and can you tell me at the network? This is an ICMPv6 type 133 message.
Shouting out to the routers on the local link.
Precisely. Third step, router advertisement RA. All routers on the local network that hear that RS message respond with a router advertisement RA message, which is ICMPv6 type 134. Okay. This RA message is central to SLAAC because it provides critical information to the host.
Like what kind of information?
It tells the host the network prefix for the local subnet. For example, 2001.db8.cafe.1.64, which defines the first 64 bits of addresses for devices on that subnet. It also implicitly provides the default gateway, which is the router's own LLA, allowing the device to send traffic off the local network. It can even include other optional information like DNS server addresses using an extension called RDNSS.
Okay, so the router gives it the network part. Then what?
Fourth step, forming the global unicast address, GUA. The device then takes the 64-bit network prefix it received from the RA, combines it with its own unique 64-bit interface ID, which it generated for its LLA, and boom, it forms a complete, unique, globally routable 128-bit IPv6 address.
So the router essentially tells the device its neighborhood address, the prefix, and its own unique house number, the interface ID. It just figures out itself using its MAC or random generation. And just like that, without a server, without manual input, it's connected to the internet.
Pretty much.
That's incredibly powerful, especially for millions of new devices.
It truly is. This four-step process enables zero-configuration internet connectivity, massively simplifying network administration. Yeah. This is especially vital for large-scale deployments and the billions of IoT devices we discussed earlier, allowing them to come online quickly and efficiently.
This sounds like a great time to talk about the Neighbor Discovery Protocol, or NDP. It's described as the Swiss Army knife of IPv6. What makes it so versatile, consolidating so many functions?
NDP is a testament to IPv6's streamlined design. It consolidates the functions of several IPv4 protocols into a single elegant suite, primarily using ICMPv6 messages.
ICMPv6 doing all the work again.
It really is central. In IPv4, you needed ARP for address resolution, ICMP for router discovery, and elements of DHCP for local configuration. NDP effectively handles all of this, making local link operations much more robust.
So ICMPv6 is much more sophisticated and critical than ICMPv4. It's not just for ping and error messages.
Absolutely. ICMPv6 is more complicated than ICMPv4 due to this protocol consolidation and the additional messages it encompasses. It's an integral part of IPv6 and must be fully implemented by every IPv6 node. Blocking it breaks things.
Good to note. Don't block ICMPv6.
Definitely not indiscriminately. Messages are logically grouped into error messages, types 0127, like destination unreachable, packet too big, time exceeded, parameter problem, and informational messages, types 128, 2505, like echo request reply for ping and all the NDP messages. The IPv6 next header value for ICMPv6 is 58. It's not an optional extra, it's fundamental.
Okay, so it's critical. We've already touched on a couple of these, but what are the key NDP message types and functions that truly make it a Swiss Army knife?
We've just discussed router solicitation, RS, type 133, sent by hosts to discover local routers, and router advertisement, RA, type 134, sent by routers to announce their presence, network prefixes, and other link parameters. These are crucial for SLA.
Right. What about resolving MMAS addresses like ARP did in IPv4? That was a big one.
That's handled by Neighbor Solicitation, NS, Tech 135. This is a direct replacement for ARP request. A device sends an NS message, typically to that special solicited node multicast address we mentioned.
The very targeted multicast.
Exactly. To determine the link layer, MAC address of another device on the local network. It's also vital for duplicate address detection, DAD, and neighbor unreachability detection, NUD, ensuring devices on the same segment are reachable and unique.
And the response, like ARP reply.
That's the neighbor advertisement, NA, Type 136, replacing ARP reply. A device responds to an NS with an NA, providing its link layer address. It can also be sent unsolicited to update neighbor information if, for example, its AMASC address changes.
Okay, NSNA replaces ARP. What else is in the toolkit?
Finally, there's redirect, Type 137. This is sent by a router to inform a host of a more optimal first-hop router for a specific destination, basically saying, hey, you could get to that destination faster by talking to this other router on our local network instead of me.
So NDP truly is a comprehensive suite, handling local link operations from router discovery to address resolution and even basic routing hints. We even saw some packet traces and router output in our sources demonstrating this in action. Can you give us a quick conceptual walkthrough of what those packet traces highlighted?
Certainly. The diagram showed host A sending a multicast router solicitation to the FFC ZO2.2 all routers address, and router 1 responding with a unicast router advertisement containing prefixes and gateway info. For address resolution, we saw host A sending that multicast neighbor solicitation to a specific FFU2.1.F address, targeting host B, and host B responding with a unicast neighbor advertisement containing its MAs.
So you can see the messages flying back and forth.
Exactly. The packet summaries for NS ID 320 and NA ID 322 clearly illustrated the specific IPv6 types and codes, showing the destination addresses, multicast for NS, unicast for NA, and key header fields like traffic class, flow label, and hop limit, all working together. The show IPv6 neighbors output on Cisco routers then demonstrated how devices dynamically learn and maintain a table of neighbor IP to MAC address mappings, just like an ARP cache, but for IPv6.
That helps visualize the behind-the-scenes work. So SLAA is great for autonomy, but sometimes you need more centralized control over address assignment. That's where DHCPv6 comes in, correct? When that of autonomy isn't quite enough for a given network environment.
Exactly. While SLAC provides robust self-configuration, DHCPv6 provides the option for more centralized control and stateful management when network environments require it, such as in large enterprises or specific service provider scenarios where you need to track who has which address. It operates in 3 main modes.
What's the first mode, which I imagine is most like traditional IPv4 DHCP?
That's stateful DHCPv6. This functions much like traditional IPv4 DHCP. A server assigns or leases full IPv6 addresses to clients and provides all other configuration options, crucially maintaining a state for each client tracking which address is assigned to which device. It's used when strict centralized IP address management and auditing are necessary.
Okay, so the server manages everything. What's the second mode? Stateless DHCPv6. That sounds like a hybrid of SLAC and DHCP.
It is. This is a very efficient hybrid approach. Devices use SLAC to generate their own unique IPv6 addresses and learn the default gateway from router advertisements.
So they get their address themselves.
Right. However, the RA also contains specific flags. The M flag for managed address configuration and the O flag for other configuration. If the O flag is set, and M's is not, it instructs the device to contact a DHCPv6 server only for supplemental information.
Supplemental info? Like what?
This is most commonly used for things like DNS server addresses or NTP server information, without the DHCP server needing to manage the actual IPv6 addresses themselves. It's like, here's your address from SLA, but check with this other guy, DHCPv6 for the phone book, DNS.
Very efficient, leveraging the best of both worlds. And the third mode, prefix delegation. DHCPv6-PD. This sounds particularly important for ISPs and home networks.
It's absolutely critical for ISPs and for scalable home network deployment. DHCPv6-PD allows an ISP's router to automatically assign an entire IPv6 prefix, say, a 56 or a 48 block of addresses, to a customer's home router.
So the ISP gives my router a whole chunk of the internet address space.
Exactly. Your home router can then use this delegated prefix to create and manage its own internal subnets using SLA or its own stateful DHCPv6 server for devices within your home. It makes managing home networks much easier and scalable.
That's really cool, but wasn't there a catch mentioned in the Reddit source?
Yes. One of our Reddit sources did highlight a challenge here, though. The current lack of a universally standard way for customer routers to communicate their delegated prefixes back to other internal systems that might need to know them. This often leads to vendor-specific, what they call homebrew duct tape solutions, which can complicate interoperability for some advanced users trying to coordinate things internally.
So even with all these advancements, some areas are still maturing, still working out the kinks. Now let's address path MTU discovery and fragmentation in IPv6. This is another big difference from IPv4, and you mentioned earlier that routers don't fragment packets anymore.
A very important distinction, and one that greatly enhances network performance. We reiterated earlier that unlike IPv4, intermediary routers do not fragment packets in IPv6. Fragmentation is strictly performed by the source node only.
So if a router receives a packet that's too big for the next hop, it just drops it then. That seems a bit harsh.
Precisely. It drops the packet, and importantly, it sends an ICMPv6 packet too big error message type 2 back to the source.
The feedback loop again.
Right. This is the core of path MTU discovery, PMTUD, defined in RFC 1981. It enables hosts to dynamically determine the minimum maximum transmission unit, MTU size, along an entire path to a destination. The source then receives this message, learns the smaller MTU, adjusts its packet size, and retransmits the data.
So the source host is proactive in figuring out the right size rather than routers doing the heavy lifting midstream. That's a clever way to offload work from the network core.
Exactly. A node either starts by using a default MTU of 1280 bytes, which all physical networks must support as a minimum, or it uses PMTD to dynamically find the actual minimum MTU along the route. This shifts the computational burden away from the core network routers.
And when a source host does need to fragment because maybe PMTD failed or isn't fully supported end-to-end, how does that process work in IPv6 given the new header structure?
Right. If the source decides it must fragment, it uses that fragment extension header we mentioned earlier. IPv6 datagrams are conceptually divided into two parts for fragmentation by the source.
Two parts.
Yes. The unfragmentable part includes the main IPv6 header, plus any extension headers that must be present in every fragment, such as the hop-by-hop options or routing headers that need to be processed by intermediate nodes.
Okay, the essential routing stuff.
Exactly. Then there's the fragmentable part, which contains the actual data portion of the datagram and other extension headers, like authentication header, encapsulating security payload, or destination options that are only for the final destination. This fragmentable part is what gets split across multiple fragments.
We had an illustrative example in the sources showing how a datagram with a 100-byte unfragmentable part and a 270-byte fragmentable part sent over a link with a 230-byte MTU would be broken down. Can you briefly walk us through the conceptual flow of that without getting bogged down in every byte count?
Of course. The key idea is that the source host takes that original datagram. It creates multiple new fragments. Each fragment will contain a copy of the 100-byte unfragmentable part, ensuring all necessary routing information is always available at each hop.
So every fragment has the main header.
Yes, plus any essential extension headers. Then, crucially, each fragment will also contain an 8-byte fragment header. This header includes information like the original datagram's identification number and the offset of this fragment's data within the original data payload.
Tells the receiver how to put it back together.
Exactly. Finally, each fragment carries a portion of the 270-byte fragmentable part, sized appropriately for the link MTU, minus the headers, until all the original data is sent. This process ensures that while routers don't fragment, the source can still send large amounts of data across paths with varying MTUs, letting the destination reassemble it.
That makes the process much clearer. The source does the work, using that special header. And finally, our sources also mention that each IPv6 host maintains a set of caches and lists to facilitate these processes, like a neighbor cache, destination cache, prefix list, and various timers.
Yes, this ICMPv6 model host architecture is really what enables the device to be so intelligent and self-organizing. By maintaining these caches and lists, like the neighbor cache for IP to MAC mappings, the destination cache for path MTUs and next hop information, the prefix list learned from RAs, and the default router list, the host can efficiently manage neighbor reachability, address resolution, MTU discovery, and overall network state. It's a key part of IPv6's self-organizing and resilient nature.
All right, so we've covered the why and how of IPv6, from its massive address space to its streamlined protocols. Now let's talk about the journey from here to there, the great transition from IPv4 to IPv6. It's abundantly clear the internet can't just flip a switch, so coexistence is absolutely key.
Absolutely. The Internet cannot simply switch off IPv4 overnight. The two protocols must coexist and interoperate for many years, likely decades. This transition period relies on several key strategies to manage that complex evolution.
What's the most common and arguably the most elegant approach to this coexistence, the one most networks aim for?
That would be dual stack. This is the most common and widely preferred strategy, where devices, routers, and servers run both IPv4 and IPv6 protocol stacks simultaneously. A dual-stack device essentially has both types of addresses assigned to its network interfaces.
So it speaks both languages.
Exactly. When it wants to connect to a destination, say google.com, it queries DNS for both an IPv4 record and an IPv6 AAA record address. It's configured to prefer IPv6 if available.
Prefer the new one.
Right. But it will seamlessly fall back to IPv4 if the destination is only IPv4 enabled. Most modern operating systems and network hardware are dual-stack capable right out of the box.
So my phone or laptop likely has both types of addresses right now, trying to use IPv6, but ready to switch to IPv4 if needed. That's quite transparent for the end user.
Exactly. It's designed to be transparent and as frictionless as possible to the user, allowing for a gradual adoption across the Internet. You usually don't even notice which one you're using.
Okay, dual stack makes sense. What about tunneling? That sounds like a way to bridge the gap when parts of the network aren't ready for IPv6, like building a temporary bridge.
Tunneling is exactly that, a method to carry IPv6 traffic over IPv4-only infrastructure by encapsulating an entire IPv6 packet inside an IPv4 packet. Think of it like putting an IPv6 letter inside an IPv4 envelope.
An envelope within an envelope.
Pretty much. The IPv4 packet is then routed across the IPv4 internet until it reaches a tunnel endpoint where the IPv4 envelope is removed, and the original IPv6 packet continues its journey on an IPv6-enabled network.
So it's a workaround for IPv6 communication when the underlying network only understands IPv4, almost like a secret passage.
Precisely. Examples include protocols like 6 and 4, Teredo, and ISATAP. While ingenious and vital during the early stages of transition, tunneling is generally viewed as a transitional tool, not a permanent solution, as it can add latency, complexity to network operations, and sometimes create new points of failure or security concerns if not managed properly.
So, useful, but maybe not ideal long-term. And finally, translation. How does that work to allow communication between fundamentally different protocol versions? This isn't just tunneling, it's actually changing the packet.
Right. Translation allows for direct communication between IPv6-only devices and IPv4-only devices by actually rewriting the packet headers. The most important mechanism here is NAT64. A NAT64 gateway sits at the border of an IPv6 network and the IPv4 internet.
Like the NAT we talked about earlier, but between v6 and v4.
Sort of, yes. It effectively translates IPv6 packet headers into IPv4 headers for outgoing traffic, and vice versa for return traffic, maintaining state just like regular NAT. This is often used in conjunction with DNS64.
DNS64, what does that do?
DNS64 is a DNS server that works with NT664. When an IPv6-only client asks for the address of an IPv4-only server, the DNS64 server doesn't just say not found. Instead, it synthesizes a fake IPv6 address that actually points the client towards the NAT64 gateway.
Clever. So it tricked the IPv6 client into sending traffic to the translator.
Exactly. The client sends its IPv6 packet to this synthesized address, the NAT64 gateway.
Yeah.
The gateway translates it to IPv4, sends it to the real destination, gets the IPv4 response, translates it back to IPv6, and sends it to the original client.
So an IPv6-only phone, for example, can still access an old IPv4-only website seamlessly.
Exactly. This combination is heavily used by mobile carriers, for instance, to operate IPv6-only internal networks for efficiency and address abundance, while still providing their users full access to the legacy IPv4 internet. It's a testament to the ingenuity of network engineers in bridging these two worlds.
It sounds like the transition is being driven by some very real, very pressing needs. What are the main drivers of adoption for IPv6 right now? Where are we seeing the biggest push?
The biggest drivers are undeniably the Internet of Things, IoT, and mobile networks.
Makes sense, given the sheer number of devices.
Absolutely. The IoT represents billions and soon trillions of small connected devices. Assigning a unique routable IP address to every sensor, every smart appliance, every piece of industrial equipment is simply impossible and unsustainable with IPv4's limited address space and the complexities of NAT. IPv6's massive address space is the only viable solution for this scale.
And SLAC, that self-configuration we talked about, must be perfect for these devices too. They're often low power and don't have complex management systems. You just plug them in and they get an address.
Absolutely. Features like SLAA are ideal for low-power, self-configuring IoT devices, allowing them to come online with minimal overhead and no manual intervention. Then there's the mobile and 5G momentum. Mobile networks are among the largest and fastest-growing segments of the Internet.
Huge user bases.
Huge. Mobile carriers face immense operational challenges managing IPv4 scarcity and complex multi-layered NAC deployments, carrier-grade NAT or CGN, for hundreds of millions of subscribers. The operational costs and performance bottlenecks were becoming unsustainable.
So they're truly seeing the pain points of IPv4 firsthand, where it hits their bottom line and affects user experience.
Yes, that's why many major carriers globally now run IPv6-only internal networks, using NE64 only when users need to access legacy IPv4 content. The ongoing rollout of 5G, connecting even more devices with stricter performance requirements and higher bandwidth demands, further intensifies the reliance on an IPv6 core to provide seamless, scalable connectivity.
So this isn't just a theoretical upgrade. It's a practical, business-driven necessity that's actively being deployed, especially in mobile. But what about the current status and challenges? Is it smooth sailing for IPv6 everywhere?
Not entirely. While the transition has been a slow and steady marathon, it is undoubtedly accelerating now. Google's metrics, for example, consistently show over 50% IPv6 adoption in the US and is growing globally.
Over 50% in the US. That's pretty significant.
It is. And the U.S. Department of Defense even has a mandate to be 80% IPv6 only by the end of 2025, with impressive progress already. But as our Reddit discussion highlighted, there are still significant perceptions of complexity that create hurdles.
Yes. The Reddit thread really gave us a glimpse into the human side of this. What were some of the common user frustrations about IPv6 mentioned there? Things that make people say it's too complicated.
Many users found IPv6 addresses scary long, messy, and genuinely difficult to remember or work with compared to the shorter, familiar IPv4 format. There's a certain human comfort with those four numbers in dotted decimal.
Yeah, 192.168.1.1 is easy. Fee 80, not so much.
Right. This often translates into a general perception that IPv6 is just inherently too complicated.
And what about professional inertia? Do network engineers feel the same way, or is it different for them?
That sentiment was certainly present in the discussion, but often nuanced. Some admitted, maybe half-jokingly, that older network engineers might be too busy to learn something new, or that a simple lack of practice contributes to the perceived difficulty, rather than inherent complexity. Once you work with it, it often clicks.
So it's the learning curve?
Partly, yes. There was also a strong security by obscurity concern voiced. Some felt that NAT in IPv4 provided a perceived, albeit flawed, layer of security for internal networks by hiding devices. Without NAT in IPv6, devices feel more exposed and require more diligent, explicit firewalling.
Those are all valid human concerns. But were there strong counter-arguments and benefits highlighted in the discussion that address these points? Did the engineers push back?
Absolutely. Many argued that IPv6 is often much simpler than IPv4 once that paradigm shift, like truly understanding the absence of NAT and the power of auto-configuration, is grasped.
Simpler. How so?
They suggested that for network engineers, it can actually simplify network design significantly. No more complex subnetting math, no more fighting for private IP space. A helpful mental trick mentioned was to think of IPv6 addresses as two distinct 64-bit parts, one for the route subnet and one for the interface host. That makes it feel more manageable.
That helps make it less daunting conceptually. What about the memorization issue, the scary long addresses? How do they counter that?
The consensus was strong. Users and administrators should and will rely on DNS or MDNS for local networks for addressing, rather than trying to memorize IPv6 addresses.
Just like we do now for websites.
Exactly. That's what DNS is for. We rarely type in IPv4 addresses directly anymore either. And regarding hexadecimal notation, they reiterated it's more consistent and functional for longer addresses than decimal would be, making it easier for machines to parse and manage.
So it's less about inherent complexity and more about unfamiliarity with a new paradigm, maybe mixed with some resistance to change.
That's precisely it. The perceived complexity is often framed as unfamiliarity with the paradigm rather than unintelligence. In fact, the consistent use of standard 64 subnets and 48 site prefixes leads to predictable, consistent address components that can actually be easier to manage than IPv4's variable length subnet masks and the constant battle with private IP conflicts.
What about real-world hurdles? I recall a comment about turning off IPv6 to fix Windows problems. Is that still a thing?
Yes, there's anecdotal evidence and historical context there. People did turn off IPv6 to resolve Windows networking problems in the past, though often this was a workaround for underlying driver issues, misconfigurations, or poorly implemented network stacks, rather than an inherent flaw in IPv6 itself.
So blaming the protocol for a bad implementation.
Sometimes, yes. It also highlights varying levels of IPv6 support among ISPs and router vendors over the years. Some, like Unify mentioned in the thread, had inconsistent support in the past, though that's generally improving across the board now.
And the internal business case for IPv6 deployment, beyond just avoiding IPv4 exhaustion. Is it easy to justify the cost and effort?
There's an ongoing debate around that. Many argue that the real business benefits are most apparent when IPv6 replaces existing IPv4 headaches and complexities, rather than just being added on as another protocol to manage.
So if it solves a problem, it's easier to sell.
Exactly. If you're removing the need for complex NAT schemes, dealing with tiny and constrained subnets, managing painful 1.1 NAT between regions, or fixing split horizon DNS issues caused by NAT, the business case for adopting IPv6 becomes much stronger due to operational cost savings and increased agility. It's not just an IT project, it's a business enabler.
Finally, the big question from the discussion, will IPv4 ever truly be deprecated? Or will it just linger forever, especially on private networks?
There are definitely two camps on this. Some argue that private IPv4 will be around for a very long time, perhaps indefinitely, especially for internal networks that are isolated from the public internet and just work. Why change it?
If it ain't broke.
Kind of. Others believe that for the public internet, full deprecation is inevitable and necessary, pointing to large players like mobile carriers already moving towards IPv6 only and major cloud providers starting to charge for public IPv4 addresses. It's a marathon, as we said, but the direction for the global public internet seems clear towards IPv6 dominance. Private networks might lag behind.
So while the transition has its challenges and perceptions, the underlying advantages and very real-world demands are driving its adoption, especially in crucial areas like mobile and IoT. That brings us to a final vital point, security in the IPv6 world. How does IPv6 stack up, given its new design? Was it built with security in mind?
It's important to understand that IPv6 was indeed designed with security considerations integrated from the start, providing new capabilities but also introducing new considerations. It's not inherently more secure as a magic bullet, but it certainly offers a stronger foundation and mandates, or at least strong recommendations, for certain security features.
And a big part of that foundation is IPsec, Internet Protocol Security, right? You mentioned the AH and ESP headers.
Indeed. IPsec was originally mandatory in the core IPv6 specifications, though it's now technically a strong recommendation that's very often implemented, especially in enterprise and government contexts. Its framework is much more integral to IPv6 than it ever was to IPv4, where it was always an add-on.
So it's baked in more deeply.
Exactly. IPsec provides cryptographic security directly at the network layer, ensuring authentication, verifying the sender's identity, confidentiality, encrypting data to prevent eavesdropping, and integrity, detecting any alteration of data in transit. It's implemented via those standard extension headers, specifically the authentication header, AH, and encapsulating security payload, ESP.
So security features are not an afterthought. They're built right into the architecture in a modular way using those extension headers. But what are the new security considerations and challenges that come with IPv6's paradigm shifts? It can't all be good news.
No, there are definitely new things to think about. One major point is firewalling differences. IPv6 firewalls cannot simply block all ICMPv6 traffic, as many older IPv4 firewalls might have done with ICMPv4.
Right, because ICMPv6 is essential for NDP and SLAAC.
Exactly. Blocking it will effectively cripple an IPv6 network. Firewalls need much more granular rules to allow necessary NDP messages like RAs, RSs, NS, and packet too big messages, while still blocking potential threats like malicious redirects or unwanted echo requests.
So the old block all ICMP rule won't work anymore. You need a more intelligent, stateful firewall that understands ICMPv6.
Correct. It requires a more nuanced approach. Then there's the end of security by obscurity.
We touched on this from the Reddit thread.
Yes. In a native IPv4 network, internal devices aren't directly reachable from the internet, which offers a flawed but often perceived layer of protection. In the net-free world of IPv6, every IPv6-enabled device can, and often does, have a public global unicast address.
Directly on the internet.
Potentially, yes. This means that every device, from a critical server to a smart home gadget, is potentially exposed to the internet and must be properly secured and firewalled at the host itself or the network edge. The responsibility shifts more towards endpoint security and proper network segmentation.
That's a significant shift in mindset for many administrators and users, thinking about every single device being directly reachable and needing protection.
It is a big cultural shift. Additionally, the various transition mechanisms like tunneling, 6 and 4, Teredo, and translation in AT64 can introduce new attack vectors if not configured securely or if misimplemented. They create new potential points of vulnerability.
So the bridges themselves can be weak points.
Potentially. And a specific threat often highlighted is rogue RAs or router advertisements. A malicious actor on the local network could send a fake router advertisement message, perhaps announcing itself as the default gateway or advertising a malicious DNS server.
Which could lead to a man-in-the-middle attack, redirecting traffic through the attacker.
Precisely. All local traffic could be intercepted or misdirected.
That sounds pretty serious. How do we mitigate against a threat like a rogue RA?
The key mitigation is RA Guard, a feature implemented on modern network switches. It allows administrators to specifically configure switch ports, designating which ports are trusted to send router advertisement messages, usually only the uplink ports connected to legitimate routers, and which are not, like ports connected to end-user devices.
So the switch blocks fake RAs from untrusted ports.
Exactly. It prevents unauthorized or malicious router announcements from being accepted on the network. So while new challenges emerge with IPv6, the protocol ecosystem also comes with sophisticated tools and design principles to address them effectively, though it requires a proactive and knowledgeable approach from network managers.
Wow, what an incredible deep dive into IPv6. It's truly more than just more addresses, as we initially promised. It's a foundational shift in how the internet works, touching almost every aspect of network communication.
Indeed. We've seen how IPv6's monumental address space solves the critical IPv4 exhaustion problem, which was becoming an existential threat to internet growth. We've seen how its streamlined header and modular extension headers boost performance and flexibility.
Getting rid of things like the header checksum and router fragmentation.
Exactly. And how its intelligent multicast capabilities enhance network efficiency by replacing inefficient broadcast, which is great for streaming and conferencing applications.
And the magic of self-configuration through SLAAC and the comprehensive nature of the neighbor discovery protocol really make IPv6 networks more autonomous and robust, massively simplifying network administration, especially for things like IoT.
Plus, we've walked through the ongoing transition, driven by the insatiable demands of mobile and IoT, and the various coexistence mechanisms, dual stack, tunneling, translation ensuring a smooth, if sometimes challenging, evolution.
It's a protocol built for tomorrow, solving the scaling problems of today and enabling future innovations we can only begin to imagine.
That's a great way to summarize it.
Absolutely. And it's important for you, the listener, to remember that even if invisible, IPv6 is increasingly the backbone supporting your daily digital lives. From streaming media to connecting your smart devices, especially on mobile networks where adoption is often highest.
You might be using it right now and not even know it.
Exactly. It truly restores that original architectural elegance of the internet, enabling a truly global network where every device can potentially be a first-class citizen with direct end-to-end communication, freeing us from the workarounds and complexities of the NAT-constrained IPv4 world.
And that, I think, leaves us with a truly thought-provoking question, building on all we've discussed today about this restored end-to-end vision and limitless scale.
All right, let's hear it. What should we leave our listeners thinking about?
As the internet fully embraces IPv6 and literally every device on the planet can have its own globally unique address, consider this. What entirely new paradigms of distributed computing, true peer-to-peer applications, or even global, secure, self-organizing mesh networks might emerge when the concept of address shortage becomes a completely forgotten relic of the past? What happens when connectivity is truly ubiquitous and direct, opening up potentially boundless possibilities for connection and innovation?
Wow. That's a powerful thought to end on, a truly limitless internet moving beyond just connecting people to connecting everything directly. Thank you for joining us on this deep dive. We hope you feel much more informed and ready for the IPv6 future.